We've made it to chapter 8. We are starting something totally different in this chapter. This is going to be over center of gravity and centroids. Now the center of gravity, let's write this word out. So center of gravity, and it has a symbol. So the symbol kind of looks like that. So kind of like that BMW symbol that you see on the cars. The center of gravity, what that is, that's the point where a body's gravitational attraction acts. That's all it is. All right, and then to go over that, what we're going to do is we're going to consider a case of a wooden board or a beam. All right, so this is a uniform beam, so assume it's nice and symmetric here. And what we're going to do is we're going to put a point here right in the middle. And at this point, if you rest this right in the middle of the beam, which the way I have it drawn is not right in the middle, but if it's right in the middle, the wooden board is going to be perfectly balanced at this point. All right, so there's not going to be any rotation. It's just balanced perfectly at this point. Let's go ahead and I'm going to measure to that point. And I'm going to call that X bar. So X bar just measures out to this point where we've got the beam balanced. Let's call that point O. Now, what I'm going to do is we're going to work our way across this little board and we're going to look at the different particles. So this board is made up of a bunch of particles and I'm just going to kind of go through here and we're going to pull out a few of them. So let's say we have this piece right here. Let's call it weight 1. That would be M1 times G. Now let's move over here a little bit. We got weight 2. That's going to be M2 times G. Then we can come all the way over here to the right. Let's say it's WN, so weight N. Now that, you could probably guess, is MN times G. So we're just looking at all these little particles. They've all got a weight. And now what I want to do is from this left side, I want to measure to those weights. All right, so to this first one right here, I'm going to have my measurement, and that's going to be X1, and let's put the little tilde on top. We'll do the same thing over to the second one right here. That one will be X2 with the little tilde. And then finally we'll come all the way over to the nth one. So over to here. This distance is xn with the tilde. So all we're doing is we're measuring to these little particles of the wooden board. No big deal. Now let's say we want to do equilibrium, because remember we said this was going to be perfectly balanced. It's not moving, it's just sitting here, it's balanced perfectly. That means we've got equilibrium. So for equilibrium, we know the sum of the moments about our point O has to be equal to 0. So now what we're going to do, let's go ahead and let's calculate the moments for our points here about point O. So if we do that, let's start with W1 first. Counterclockwise is still positive. If we find the moment of this, we're going to have weight 1, and then our distance is going to be from here over to here. That means we're going to have X bar minus this X1 tilde. All right, so that's our moment arm. Go to W2, do the same thing. That's still a positive moment. So we're going to plus W2. Now this distance is going to be from here over to here. That's X bar minus X2 tilde. Like that. And then you're just going to keep going. All right, so you'll keep going. We'll come over to here. Now we've got WN. And now this distance is this to here. So right there. Now just to keep this as positive, I'm going to write this as X bar minus XN tilde. That will give you a negative moment because XN is larger than X bar. All right, I'm just trying to keep these in the same order. All right, so the signs would work out in the end. Now we've got that. So all we did was find our equilibrium equation, found a moment about point O. Now we can go through here and rewrite this in summation form. We'd have the summation. Let's start k equal to 1. We're going to go up to n. And we're going to have mk times gravity. That gives us our weight times x bar minus xk tilde. That equals 0. All right, all we did, rewrite this in summation form. No big deal. Let's extend this out, and let's split this up into two terms now. Let's pull g out because that's constant for all of them, so we'll have g, multiply that by the sum. We're still going from 1 to n. And let's have mk times x bar. And now let's subtract that from g times the sum, going from k equals 1 to n of mk xk tilde. That's 0 still. Okay, so all we're doing is splitting this up. Nothing too exciting there going on. Now what we've got gravity here. That's the same gravity. So if you look, let's put an arrow there. Now that we have this equation, we can take one of these to the other side, cancel out gravity. And if we do that, we get the summation, oops, from 1 to n of mk x bar. That's got to equal the sum from k equal 1 to n of mk xk tilde. So you have to have this requirement for equilibrium. And now what we want to do is we want to find x bar. So let's solve for x bar. If we do that, we get the summation k equals 1 to n of mk xk tilde. We're going to divide that by the sum going from 1 to n of mk. So now if you look at what we've got here, this top part is going to be the sum of the moments about O. That's the part where we get that from, and then you divide that by your total mass. All right. Now this x bar, what that is your center of mass location. Okay, so all the center of mass is, it just tells you where your gravity can work, all right, where it's going to act. That's all it's telling you. Okay, so here you saw at the beam, x bar went to this balancing point. All right, so that should have been drawn like more over here, so it's in the center, but it's just where we're going to assume gravity acts. And x bar is the notation that we'll use for the x direction. So like this, you could go through and do the same thing for the y-axis and then the z-axis. And that'll give you your center of mass equations. So basically what we're going to have x bar equals the sum of x tilde m over the sum of the masses. And then y bar, we'd have the summation of y tilde times the mass over the sum of the masses. And finally, z bar, if we had a 3D case, we'd have the summation of z tilde times the mass over the sum of the masses. So notice gravity is not in these equations, so your center of mass is independent of gravity. Okay, so you got x bar, y bar, and z bar. Now, if you want to look and see what that kind of tells you, there you go. Basically those, if we go to the 3D case first, those are just going to be essentially the coordinates of your center of mass for your system. Okay, And then here's what you'd have in the 2D case. So x bar is the direction in the x on the x-axis, y bar is the one in the y direction. All right, so we've got those equations. Now the problem is we're dealing with rigid bodies. A rigid body is going to have an infinite number of particles. So are you really going to be able to sit there and do all of these calculations for an infinite number of particles? You're going to be able to go through and do, find x tilde times the mass for all of the particles? No, you're not going to be able to do that. So because of that, we're going to use integration, and that's going to lead us to centroids of areas. Okay, so let's talk about centroids of areas. And we're going to be using bodies made of uniform material. So if we say we have a wire, we're going to assume the wire is the same material throughout. It's the same thickness. There's no sort of variation in the material. All right, so that's the assumption we're going to make. Now our center of mass for this type of case is going to be called the centroid. All right. So that's all it is. So whenever you hear centroid, just know you've got a rigid body, it's got uniform material. And the centroid is just basically where the center of mass is. Now our centroid is going to be a feature of geometry, not the material. All right, so keep that in mind. So we don't really care if it's aluminum or lead, whatever. We don't really care about that. We care more about the geometry of the body. Okay, so let's look at this little drawing here. I've got this body drawn, and it's going to be made up of all of these little areas. So I've got like an A1 here, A2, I've got AN. This capital A just represents the total area. All right. Now what we're going to do is you can come through here and let's draw out another coordinate system. We got X and Y. Let's draw this shape again. Now for each of these little areas, let's call it DA, we can find the X tilde value. All right, so for each of the little areas, remember X tilde and Y tilde from the last one, it's just going to be your location to that tiny little area. All right, so now if you do this for all of the different areas, you can see them all in here. If we do this for all of them, then what you'll get when you use our equations is you'll get the location of the centroid. So let's put this is our centroid symbol. It might not look like it, but that's what it was supposed to be. There's our area. So now after you do all of those little DA areas, you're going to have X bar and then Y bar. All right, now similar to our center of mass equations, here we're using area, but our equations are going to be very similar. We're going to have X bar. It's going to equal the sum over the X tilde times A. And this is for all of the little areas. You're going to put that over the summation of the areas. So this gives you the total area. That's for X bar. Y bar is something similar. You'll have YI tilde times AI. Put that over the total area. Then finally Z bar. So that'll be the sum of Z tilde times A over the total area. All right, so now we've got that. So let's go ahead and then look at this. Now we already said, just like up here with the rigid body, we have the infinite number of particles. Right here we said that. Down here we have an infinite number of little areas. Okay, so here I just drew this little grid so you could see it split up. But there could be an infinite number of those areas. And we don't want to sit there and go through and measure all of these things. All right, so that's going to lead us to our integration equations. All right, let's put these equations on the next page. All right, so the first ones we're going to talk about, these will be called area centroids. So this is when we're looking at the little dAs. We have an area. We're going to have integration forms of those equations. X bar is then going to be the integral over the area of x tilde dA over the integral of dA. Y bar is going to be the integral over the area y tilde dA over the integral of dA. And then z bar is going to be the integral of z tilde dA over the integral dA. Those are your area centroid equations. Now we also have equations for volumes and lines. Volume centroid is going to be where we have a volume that we're looking at. So let's think of like a cone, for example. We have something like that. All right, so not just an area, but we have a cone. We can find the centroid of that volume. And our equation here is going to be very similar to what it was up here, except for now we're going to have volume instead of area. So we'll have the integral over the volume of x tilde dv over the integral of dv, and then y bar, you can probably figure out what these are going to be by now. We'll have the integral over the volume of y tilde dv over the integral of dv, and then z bar, we'll have the integral of z tilde dv over the integral of dv. Those will be our volume equations. Finally, line centroids. These are going to be used whenever you have a thin rod or a wire, something like that. All right, so if we want to draw a little picture, let's just say we have some sort of wire. Looks like this. So in the equation we have dl, so just think of pulling out a tiny little length of this wire, and then you're going to find the x tilde, the y tilde, and then the z tilde for that little area, for the little length. So for the line centroid, we're going to have x bar equals the integral over the length of that line of x tilde dl over the integral of dl. Y bar is going to be the integral of y tilde dl over the integral of dl, and then finally z bar will be z tilde dl over the integral of dl. Those will be your equations for a line. Okay. Now once you see the examples, you'll see these aren't too bad. So I know you might be getting worried about the integrals with the x tilde, y tilde, and all that, but I promise you they're not too bad. Now centroids are going to be easy to find if your object is symmetric. All right, so if you think about it, let's say we have something that looks like this. And let's draw something that looks like a flower. All right, this is supposed to be symmetric, but y'all know I can't draw symmetric things. If this was nice and perfectly symmetric, then we know where the center of mass is going to be. It's going to be right in the center. Okay, so if it's symmetric, it's going to be pretty easy to figure out where your center of mass is, or your centroid. So just keep that in mind. And then also one more thing I want to point out, if you've got circular boundaries, so if you're doing a circle or a semicircle, something like that, polar coordinates will be your friend. You want to use those polar coordinates. All right. So let's stop this video here. We'll pick it up in the next one with an example.